and this will be true, and this will be true. Okay? So that kind of R is called an equivalence relation. Okay? And instead of using R here, we use a special symbol called tilde, T-I-L-D-E, in other words, just like a wiggle, or just one sine wave, just one wave, up, down, right? Tilde, here. So now an equivalence relation, all three of these possibilities are true. You know, that this, and this is true for an equivalence relation. So instead of writing R, we write this tilde, okay? So x tilde x. So a relation exists between itself, between x and x. Now that's this case here, right? And if that's true, if this relation, equivalence relation, holds between x and itself, this property is called reflexive. It's sort of like a reflection in a mirror, right? XX, okay? Now, if an equivalence relation exists between x and y, two members of your set, then now remember that it's an ordered pair, then that equivalence relation exists between y and x. And if that's true, this relation here is said to be symmetric, right? There's a kind of symmetry, right? X, y, y, x, same. So that property of that relation is said to be symmetric if that equals that, right? Symmetric. Now, if this relation, tilde, whatever it is, if that holds between x and y, and between y and z, then it also holds between x and z. Now, transitive. Trans just means across, right? So you're going across from y to z, right? So you sort of like two steps. So this relation here is said to be transitive if this and this gives you this, right? Now, if you have all three, this relation here is called an equivalence relation. And why is that? Well, if you have a relation between pairs x and y, x, y, z, that have all three of these properties, then they're sort of the same. So that's why I use this word equivalence. So it's sort of roughly these pairs x, y, they're the same somehow. They have certain properties in common. So that's why you use this word equivalence, right? So an equivalence relation obeys these three properties. An equivalence relation is reflexive, symmetric, and transitive. It has these three properties, right? Okay, now let's actually do some examples. Now a relation a relation holds between pairs of elements of a set. Okay, so you have to specify the set. A relation on its own it's sort of meaningless. You have a relation exists between elements. So which elements? Well, you have to specify the set. Okay, all right. So let's do some examples and show that this relation, which I have to specify, but so I have to specify what the relation is. I also have to specify what the set is. So let the set A here be the people living in Xiamen. Xiamen's the city I live in on the southeast coast of China, right? So I'm trying to make the city well known. I mean, if these lecture series really take off in the future, and they'll be there on YouTube forever, right? Decades. So I hope large numbers of people in the future will follow these lectures, and hence they will learn about Xiamen. So I'm hoping to put the city on the map, the world map. Right? Okay. So let A be all the people living in Xiamen, right? And the relation between any two people, any two members of this set, okay? And that relation is born the same year. They were born in the same year. So is your question, is this relation here an equivalence relation? In other words, does it obey these three conditions? Does it have these three properties? In other words, is this relation, born in the same year, is it reflexive, symmetric, and transitive? That's the exercise. That's the question, all right? So if person X is that person born in the same year as himself, of course, right? So therefore reflexive. Okay. Now, if person X is born in the same year as person Y, well, obviously person Y is born in the same year as person X. Okay, that's just common sense. So yes, symmetric. Okay. Now, if person X is born in the same year as Y and person Y is born in the same year as Z, then common sense says person X is born in the same year as person Z. So yes, so transitive. Okay, so we've got all three properties. Therefore, this relation here, born in the same year, for this set, people living in Xiamen, that relation is reflexive, symmetric, and transitive, and therefore it's an equivalence relation. A special kind of relation. It's an equivalence relation, right? Now, so that's more where the set's people. Let's try a set related to numbers. Okay. So now let the set just be the set of integers, right? Z, and X and Y are just any two members of Z, any two integers, and the relation is that 5 divides the difference between these two. Okay, that's your relation. Now, question: is it this relation here? 5 divides, divs. It's just my shorthand way of saying divides. So 5 divides x minus y. That relation, the tilde, is it an equivalence relation? In other words, is this relation here reflexive, symmetric, and transitive? Okay, well, let's do the test. Now, you may remember the definition of a, what's the word? Congruent. Two numbers are congruent if so two numbers are congruent mod something if the something divides the difference, right? So if 5 divides x minus y, you can rewrite it. It's the same thing. That x is congruent to y mod 5, right? So let's show that this relation here is an equivalent relation. So we have to test this, and this. Okay? Well, how about reflexive? What is x minus x? Right? X tilde x. Well, that would be 5 divides x minus x. Well, x minus x is 0, and 5 does divide 0. Right? 5 does divide 0. So that's okay. Tick. Yeah, tick. So it's reflexive. Now, how about symmetric? Is it symmetric? Well, if x minus y, if 5 divides x minus y, you can write x minus y as 5 times some integer k. So you can write it in this form. X minus y is 5k. Now that implies that y minus x is minus 5k, right? And that means that 5 divides this, right? Here's your factor, 5. And the quotient is minus k. So 5 does divide y minus k. And hence, that's true, right? Y tilde x, because 5 does divide that, right? Okay, so tick, so symmetric, that property holds. Now, how about transitive? Does it go across? Right? So, if x tilde y, well, that implies that x minus y is of this form, let's say 5k, and you're given this also, so y tilde z, so that implies that y minus z is 5 times some integer, let's call it p, right? So y minus z is 5p. Now if you add x minus y and y minus z, the y's cancel and you'll get x minus z. Now you add, so if you're adding that and adding this, so you've got 5k plus 5p, well that's 5 into k plus p. That means that 5 is a factor of this. Okay? So 5 divides x minus z, right? And that means this relation holds between x and z. Right? 5 divides x minus z. Okay, so we've got transitive. So we've got all three. So this relation is reflexive, symmetric, and transitive, and therefore this relation is an equivalence relation, right? Because it satisfies all three properties. All right. How about A being a set of people? The relation is a friend of. Is that an equivalence relation? Well, it's not transitive, right? This relation is not transitive because we did it before up here. So if x is a friend of y, right, that's the relation, that's your tilde. If x is a friend of y and y is a friend of z, it does not follow that x is a friend of z. Right? Just common sense. So your transitive property fails. Now, if just one of these three fails, the whole thing fails. Right? You have to have all three properties being satisfied. Okay. So if one of them fails, it's not an equivalent relation. This relation is not an equivalence relation. Okay. It's not transitive. Therefore, it's not an equivalence relation. All right. Now let's do some counter examples. Well, we just did one here. Here's another one. Okay, so the set is integers again, just A is z, right? And the relation is now that 5 divides 2x minus y, right? And x and y are integers. Now, if we can just find one counterexample, so let's say x is 1. Well, does 5 divide... well, hold on. We're testing with a tilde, which is this. That's your relation. Is it an equivalence relation? In other words, is it reflexive? Is it symmetric? Is it transitive? Well, let's test. Is it reflexive? So is it true that x tilde x? Now, if that's true, your y here is now x, right? So that means you would have 2x minus x, and that's and if x is 1, you just, I mean, x can be any member of your integers, right? So it has to be true for all members of your set A, in other words, set Z. So let's take the number 1 from this set, and so 2x minus x is just 1. Right? Now, does 5 divide 1? No, it doesn't. Therefore, the reflexive property for this relation fails, and therefore this relation is not an equivalence relation. Right? Okay. All right. New concept. So you've got the idea now, I hope, of